folks. You are in a treat today. We have one of our brightest, professors in our department, Ramtin Zand here. Um, he's, I mean, highly, I think, influential in his area. He has won an NSF career grant, which is a kind of mark of big success, and other grants also. So very active in the research, has a fantastic research group. I can tell by interacting with his research students that they are really enjoying their time with him and learning a lot. So everything that you can expect for a wonderful academic research lab. He works on very attractive areas, particularly involves more hardware-centric aspects also, not just the pure system and hardware-centric aspects. And last time he gave this talk about a year ago, not this talk, in describing research about a year ago. It was one of the best lectures in our seminar series, and I expect no less this time. So to you.
Thank you. Thank you for the kind words. It's always great to be here, and I see familiar faces. Most of you took my class, so that makes it easier. Half of you are from my lab, so it makes it even easier. Okay, so today, if this works, which seems it's working, we're going to talk about Edge-Centric LLMs. And this is the word that part of it, on the hardware side, fundamentals of it started with my former PhD student. He's now a senior system designer at AMD. Started, but not in the context of large language models. And then Gene joined our lab a few months ago, I would say more than 6 months ago. And we started this kind of research on take it to the large language models and see what we want to do with it. So thank you for that and all the contributions that you're having to this project. Now, large language models. So I think most of you, especially in this building, have heard about large language models and their benefits and how exciting they are. If you scratch the surface, you're going to see them on many chatbots. Here you can see OpenAI, ChatGPT, Perplexity, Grok, and so on. But as I said, that's the surface. So if you go deeper, only in our lab, we're working on many projects that benefit from large language models. Okay, we have a project on using large language models for sign language translation. At NSF on the project, there's another project that we're taking large language models, integrating the so-called robot to teach students metacognitive skills. And this is an exciting project that they've started recently called From LLMs for LLMs. This is a collaboration with New Jersey Institute of Technology. And we are using large language models to design hardware to accelerate large language models. Okay. So everything is great, right? So large language models are very good, many applications, real-world applications. But the natural question is, what is the catch? There should be a catch, right? Life doesn't work that way. When things are good, it should be a problem. Now, we can answer this question in many different ways. We can talk about ethical concerns of large language models, many purposes, right? But today I'm going to talk about sustainability, all right? So sustainability challenges are important in terms of the energy profile, in terms of the carbon dioxide equivalent emission of these kind of models. Now, when we talk about sustainability, what do we really talk about? So this is a work, one of the earliest works in the field that focused on the sustainability concerns of LLMs. This is done by Dave Patterson. So those of you who do computer architecture with me, the course that we teach, we use Dave Patterson's book. And they have done some sustainability research on large language models. They have very interesting statistics in their paper. This is a one about GPT-3, you can see that. Okay. So GPT-3 was just out at the time. It's very early times for GPT-3. It's so early that in the paper, if you read it, they say that the paper came out, it's very exciting. So far, it has 700 citations. Now it has like 35,000, 40,000 last time I checked. Also, beyond citations, it's literally used for ChatGPT, right? If you don't pay for ChatGPT after sometimes when you're using GPT-4, it goes back to GPT-3. So it's a very useful tool. But now, if you look at how much energy we need to consume and how many accelerator years we need to train these models, the numbers are very interesting. So we have over 1,200 megawatt hour of energy that we consume. We have over 550 tons of carbon dioxide equivalent. Okay, we don't literally have carbon dioxide emission. We have an equivalent carbon dioxide equivalent emission for training, and we need 405 years of V100 GPUs. Now you can make a case that GPUs are a lot better now. We can also make a case that LLMs are a lot larger too. Okay, and anyway, it's a very big number. So no one used 405 years of that. Obviously means that they had tens of thousands of GPUs to train this model. Okay, it's a pretty big fleet of GPUs you need for training these sets. Now everyone likes to compare training machine learning models with flights. So here we go. I have one for you. As there was a paper in 2024 that compared the training of T5 model with a flight between San Francisco and New York, a round trip. It's a pretty long flight, 4 or 5 hours at least. And you generate 40% more carbon emission compared to that flight for training T5. Okay, not so great. Now, this is not just training.
Yeah.
Okay, we can try it. Things working out. That's it.
Yeah, like the internet is back. There's, but then this one is on the, it has to be on the same network.
Oh,
It has to be on the same network for
Yeah.
the
it
screen
is, it
mirroring.
is it or not?
It is, but
Okay.
like this one, this particular network is a bit slow right now. Let me call Ritik.
Mm.
Yeah,
It is strange that how you
Go ahead, maybe. This is worse. This is better. Just
Okay.
your room is fine.
You don't understand?
Oh, okay.
With the other internet connection.
Both are slow today.
Yeah, that's working. Okay, perfect. So I was saying that training is bad. Okay, let's go a little bit faster. Now inference is bad too, because based on some data that we can see, we have a lot of prompts. This goes back to 2023. We have 11 million prompts per hour. Now it makes the inference a challenge here. Okay, we have to go a little bit faster. Now what can we do about this? So energy efficiency, what we do about, energy profiles of and footprints of these guys. So you can answer this question in many different ways. You can make the network better, for example. You can make better GPUs. That can all help. But what we are interested in making models smaller, what we call model compression and optimization. Now this can benefit us in many different ways. Besides improving the energy footprint and memory footprint of these devices, this provides an opportunity for us to move these models to tiny lists. That we have a large network, instead of deploying everything on the data center, you can offload some of the workload to the edge of the network, right? So that can help overall with the entire system. Now, there are many ways that you can do compression, right? There's a whole many different methods. What we are interested in, and what I'm going to talk about, well, we're interested in all of them, but what I'm going to talk about today is on quantization. But we're not talking about any kind of quantization. We're talking about a stream session. Okay. Now, so there was a paper that came out in early 2024. And it's called the 1-bit LLM era. It attracted a lot of attentions. Many people really liked it. It's getting a lot of citations. And the idea was, if we can ternarize some of the weights of large language models, not only we save memory, but also the computation changes. If you only have one negative, one zero weights, instead of doing multiplication, you can just do addition and subtraction. Okay. And in terms of hardware, addition and subtraction, if it's not floating point, it's a lot less expensive than floating point on multiplication. Okay. That was the whole idea. Now, there's a problem with that. And to understand what that problem is, we have to go a little bit deeper into the architecture of large language models. All right. Well, let's do that together. Let's demystify large language model architectures. Now, if you look at this decoder-only LLM, and why do we care about decoder-only? Because most of the well-known LLMs are decoder-only. GPT, OPT, Llama, these guys are decoder-only. Now, if you look at the decoder-only LLMs, you see a bunch of major components in them. We have these red crosses that you see here. These are matrix multiplications or math models. Then you have nonlinear functions like layer norm, softmax, and so on. If you go back to a few years ago, these nonlinear components were actually very challenging because most of the existing hardware was designed for convolutional neural networks. So when you deploy large language models on them, they are either not even possible to run it on these devices or not efficient. Okay. Great news is that time is gone. Right now we have custom hardware for these nonlinear components. So we pushed back its computation to less than 1% of the entire model. Great. Now let's look at matrix multiplications. So matrix multiplications that you see here, they look similar, but they're not similar. There are two major differences between the matrix multiplications that we have in the attention head and the matrix multiplications that we have in the projection layers and feed-forward layers. Okay, so what are the differences? One thing is type of map model. One of them is matrix spectrum multiplication, because we have a process of caching. I'm not going to go there, but you can make decoder-only models that generate one token at a time. You can cache the previous values. Because of that, if you look at these values, you can see these guys are matrix spectrum multiplications. All right. These guys, though, these are matrix multiplication. Okay. There's another difference in data flow. Data flow of attention heads, there are activation to activation data flow. There is no trainable problems in attention heads. Okay. So you get activations and multiply them with activations. In projection layers and feed-forward layers, you have wait to act math models. You have weights, trainable problems are there. You multiply that by activations, and there we go. We have wait to act vector matrix multiplication versus act-to-act matrix multiplications. Okay. Now let's go back to one-bit LLM. The one-bit LLM claims that it's 1 bit all over the model. It is not. If you dig deeper, you see that only part of the model is 1 bit. See these green process projection layers, matrix vector multiplications? Those guys are 1 bit ternary. The kind of matrix multiplications that we have in that attention net, these guys remain 8-bit, high precision. So we have a mixed precision model. Part of it is low precision, part of it is high precision. So most of you took computer architecture with me. It's a time for me to test you guys. There is a model that connects partial improvements to the overall improvement that you can get in the system. There's a law. Do you remember what that law is? Yes, that's true. Did you know that, or
Yeah, I knew it.
because she's in my lab, I thought she was cheating. Okay, so Amdahl's law. By the way, I gave this talk at USF. I asked the same question. The entire room said Amdahl's law. So I guess I'm failing with computer architecture. So sorry for that. So that's the law is called Amdahl's law. Okay. So Amdahl's law connects total performance improvement to partial improvement. Now, naturally, for us, when we see something like this, if we're getting too excited, and that's how research works, by the way. If we're getting super excited, you have to do some fundamental research to see what should be the next natural goal, right? Otherwise, you get excited and say, okay, they improved projection layers. Maybe I should focus on attention nodes. But should you, right? So that's what we wanted to do. We wanted to do an Amdahl's law analysis, and it's very simple. We just follow Amdahl's law equation. We have to find a fraction, and then we have to speed up. And through that fraction and speed up, we connect it to all improvements. Why do we do it? Because if this fraction is small, then we haven't done much. If you improve 1% of the model and the improvement is 100 million%, who cares? You're improving 1% of the model. Okay. So in this case, we wanted to see how much of the computation can be ternalized in LLMs. We call it Amdahl's law of LLMs. We wanted to know how much of the computation can be ternalized without losing accuracy. If that fraction is close to 0, then it actually makes sense to focus on attention nodes, because that's the part that's not improved. If the fraction is close to 1, then who cares about attention nodes, right? It might make sense for us to develop a hardware to take advantage of this kind of algorithmic innovation. Why? Because if you read the Microsoft paper, it says at the end of the paper, it says, yes, this is an algorithmic innovation, everything is good. But there's a call for action. It says, you guys should build the hardware for this, by the way. GPUs don't work that way. But if you have a GPU right now, most of them don't understand 1 bit. You can say it's 1 negative 1 0 from the computation point of view. It's integer, 32-bit, 8-bit, whatever it supports. So we have to build custom hardware to take advantage of this kind of benefit that we can get from here. It only makes sense to invest on building custom hardware, by the way, because it's a very expensive process. Building hardware is not cheap. It's a very expensive process. Semiconductor industry is very expensive. So if you want to build that, before building the hardware, you have to make sure that I'm improving 99% of the computation. Amdahl's law again. So that's why we came up with this kind of law. And we tested it on an infrastructure that we have in the lab. We have built TPUs before in the lab, and we have some knowledge of it. We know the tool chain of TPUs. So we use TPUs. And what we wanted to know was how much of the compute cycles and memory accesses happen in the parts that can be improved by ternarizing the ones. Okay. Now we have 2 setups. We have a cloud setup and an edge setup. These are different in terms of how big a systolic array size is. And systolic arrays, for those of you who don't know how TPU work, TPU follows a temporal data flow. Temporal data flow, the biggest difference is that usually when you work with GPUs and CPUs, you have a memory, you have a processor. A memory and a processor talk to each other. Processing elements don't talk to each other. Okay? In TPU, they do. If you do matrix vector multiplication, for example, you don't care about the partial results. You care about the total result of matrix vector multiplication. So what you do when you calculate that partial result, you don't go back to memory, you just send it to the next processing element. So when I say 32 by 36 solitary array, I mean I have 1,024 processing elements that are connected together in form of a 2D array, and these guys talk to each other. Okay. Now we have two setups, and we have different data flows. I don't want to go there. It's just too much hardware design at this point. Now, the kind of analysis we did was we wanted to calculate how many compute cycles we have and how much memory access we have in the projection layers. I remember projection layers are the parts that could be terrorized. Okay, this is the fraction. This is the F parameter in the Amdahl's law. Okay. Now, if you look at these two different setups, this is a cloud setup. In the cloud setup, we have this heat map here. On the memory accesses, you can see that actually the majority of the memory accesses happen in the projection layers. In terms of compute cycles, that's not the case. Compute cycles depends on what kind of model we're working with and how big the sequence length is. Okay, sequence length or context length are not the same thing, but in many cases are used as if they're the same thing. But it's simple words is how big of a prompt sent to the, or how big of a prompt we can send to the LLM. Okay. Now, here we have different sequence lengths. You can see that when the sequence length is pretty large, but the model is small, most of the computation happen at attention heads. Okay, so 1-bit LLM doesn't happen. Okay, now let's go and look at the edge setup. The edge setup, in both cases, memory accesses and compute cycles, the majority of the compute cycles and memory accesses happen in the projection layers. So the fraction is more than 50%. Okay, in some cases go all the way up to 99.7%. So that is great. If I have 99.7% of my computation happen in projection layers that can be terrorized, then it makes sense for me to build a hardware for that. Because then I'm improving 99.7% of my workload. Okay. So that was the first thing we learned. Now we can move these numbers and try to plot the Amdahl's law graph. These are famous Amdahl's law graph. That's how Amdahl's law looks like, by the way. But what I'm seeing here, we see two types of lines. We see dashed lines and solid lines. Dashed lines are how much total improvement we can get if we improve the projection layers. Solid lines tell us how much total improvement we get if we improve the attention heads. Okay. In case of the edge setup, you see a very trivial improvement if you focus on attention heads. So every effort on improving the attention heads without building the hardware for projection layers is nonsense. Okay, we don't care about it. It's not a big part of the computation anyways. In edge is a little bit different. You see cases for smaller models that it makes sense to focus on attention heads, and we know it from the fractions, right? We learned that some of the fractions are changing. All right, so this is where we stop the first part of the project. Now, from this point, it made sense for us to go for the edge setup and try to build a computer architecture that is built for 1-bit LLMs, but only for edge setup, because we already established for cloud setup, it doesn't make sense. Only for edge setup, we can build custom hardware that can benefit from that. But this is the part that we added two of my other PhD students, Hasib and Peyton, are here. They contributed to this paper. Still Gene is leading these papers. The first one is a fundamental paper that he led. The second one is under review right now. This is more of an architecture paper. But each of these guys have different contributions to this part of the project. I'm basically presenting their work. So I hope I do justice. Now, okay, listen. So what did we do here? We already had the TPU. Remember we said that we have the infrastructure in the lab to build TPUs. So we took this edge TPU, we added something to it that is called processing in memory, or PIM. And it's analog PIM. Okay. Now what is analog PIM? Analog PIM is a technology that is very good for accelerating wait to act vector matrix multiplications. Does it ring a bell? Projection layers literally had wait to act vector matrix multiplications, right? So it's a perfect technology to be used for that. Even better is the fact that the most reliable kind of processing in memory technology use devices, non-volatile memory, that realizes only two states, high resistance and low resistance. So if you have two of these devices, you can generate any ternary weights. With two binary values, you can generate linear values. Both of them are same resistance as 0, one of them is large, one of them is smaller is 1, and vice versa. Now, how do we implement matrix vector multiplication in these guys? These memory technologies, it's like SRAM, and it's called MRAM or RRAM, resistive RAM. The information is stored in them in form of the resistances. So this is a little bit of electrical engineering. I'm not sure if you remember that. But if you have a resistor based on Ohm's law, this is Ohm's law. If you apply voltage across this resistance, and if you measure its current, the current that you're going to get is equal to conductance, just 1 over resistance of that device, multiplied by the voltage, multiplied by the voltage. So it's doing a multiplication analog domain for this. And then there's another rule called Kirchhoff's law, current law. It means that all the currents that go to one node of the circuit are equal to the current that's going out of it. So this is the sum accumulation in the analog domain. So it implements multiply and accumulation in the analog domain using this resistive technology that can implement ternary weights. The perfect case for us to use it to implement the projection layers. Attention heads, they still have to be high precision. Not only they have to be high precisions, these guys are act-to-act matrix multiplications, not act-to-weight. PIM is not good for implementing act-to-weight because you have to keep writing to this technology every time that you're using it for inference. It's going to lead to endurance challenges. You can't rewrite on a non-volatile memory. Flash has the same problem too. Flash memory, you don't want to write to it too often. And even if you can, you're consuming a lot of energy because non-volatile memories have an energy barrier. Okay, you have to consume a lot of energy to go from one state to another state. So it makes sense for us to use the TPU, the systolic array, for the high precision part. We had the systolic array for the high precision part. For the low precision computation, we had this PIM technology. All right. Now, let's look at the specs of the hardware that we designed. We designed systolic array that is 32 by 32 systolic array. We had 8 megabytes of memory in it. We used 45 nanometer transistor technology. We could get 100 megahertz clock frequency. For TPU, clock frequencies are a lot lower than CPU, by the way. It's a very common thing. On the PIM side, we have 4 by 4 processing elements, as you can see here. And then we have 256 by 256 RM crossbars per element, per processing element. And then we also use 45 nanometer analog to digital converters, and we use 1 transistor, 1 resistor, which is the type of the cell that we use in the process. All right, now let's profile this guy. So we profile in different performance metrics. One of them is tokens per second. How many tokens you can generate per second. Now, this technology is being compared to a regular TPU. Okay, if we had a TPU who wanted to implement this one with LLMs versus what we developed, which we call TPU PIM. Okay, or PIM LLM. We have TPU LLM and TPU PIM LLM. So you can see here in every graph that I'm going to show in the next 3 slides, you can see 4 sub figures. The top figures are smaller context length. The bottom ones are larger context length. Okay. Smaller context lengths are typically used for conversational systems. Right now, my context length is pretty large because I'm talking, you guys are listening. In real world, we go back and forth, right? So that's good for a small context length. So you can see that you can get a lot of benefit, 80 times improvements for smaller context lengths for large models. For larger context lengths, it gets smaller, but still pretty high. Okay, you can get like 5 times improvement. 5 times improvement is not nothing. It's a lot faster. Okay. Now let's see what we do in terms of energy, because remember we want to deploy these guys on.
Is this for inference time?
It's inference. Everything for inference. All the discussion we're having here is for inference. This is the part that we had a Zoom connection issue. I made a case that inference is now becoming even worse than training. Actually, if you want to know that, the OpenAI's argument against DeepSeek was that they might be able to train a network, which I'm not sure it's a good argument, on it, just repeating what they said. They might be able to train a network, but they can't respond to them in prompts that we're getting. Okay, so that means that you need a fleet of hardware to respond to those inferences. Again, not my opinion, but it's a big deal. Inferences, it's a big deal. Everything is inference. Yeah. Now you remember we want to deploy these guys on embedded devices. So embedded devices are mostly powered by battery. So energy becomes important. So what the next thing we analyzed was tokens per joule. Okay, how many tokens we can get per joule. Now these numbers, you can see that the improvements are a lot less compared to the speed up that we can get. That's because pin consumes a lot of power. Okay, now, but if you want to look at it from the big picture, you have a system that could be 70 times faster and it still be 10% more energy efficient. Yeah. In cases it can be even 70% more energy efficient. So we still get energy efficiency. It's not like 80 times more. It's a little bit there. Okay. So it's a good deal, right? It's a great deal, actually. So if we can get the speed up with not significantly higher energy consumption, that's what we want. But also to put it in context. Can we yeah, I'm gonna say maybe sound their enemies. So yeah, that's distracting a little. Let me go there. Well, so what was talking about? So I'm sorry, I can't do it. I just have to do later. So tokens per joule, it's not accurate. But if we look at so let's put it in context. Joule, we get it, it's fun, but what is joule? Okay, let's talk about it in terms of battery life. Okay, so let's see how many words we can generate per battery life. So we had a conservative estimate of 1.5 tokens per word. Okay, which is typically a very conservative estimate. There are papers that have 1.04 tokens per word. Your tokenizer could be very efficient. But let's say it's 1.5. Worst case for us. Okay. And also, let's say we use a battery, like a mobile battery. Let's not even a new one. We have batteries that are a lot better than this, what you're using here. A very typical battery for a mobile device. And this is something I have to also emphasize. Assuming that we are only using that mobile device to generate words, which is not typically the case. This is something to give you some ideas. But here we're generating tens of millions of words or few millions of words per battery life. Even if you're doing something else. Worst case, that tens of millions because hundreds of thousands of words. That's a lot of words. Put it on context, a 6-page paper, or 2,000-3,000 words. Right? We don't probably I'm using like a few thousand words a day, giving a talk. So it's pretty short. Anyone ask something?
I was just saying that was just per charge of the phone. So every day you can have this much.
Yeah, so I'm going to
Right.
charge it again. That's true. So like in one charge, that's what they get. Obviously, you can charge it and use it again.
Per day you can get this many.
Yeah, per day you can get hundreds of thousands of words, which is pretty high.
Also the graphs, like you said in the last graph, this is an increasing trend with increasing size of the model. So OPT 6.7B, we see 13% improvement, but if the model gets larger, we will see 20% and more improvements. Let's say we get 30 billion, 66 billion for larger models.
So you can get, and this also can be, if you look at the fraction heat map, it's following that pattern. A little bit. So if you go back and look at that, it's the same pattern. When the models get bigger, more of the computation happens in the projection layers. Therefore, because you're including the projection layers into LLMs, we see better benefits. Thank you. So this is how many words per battery life we have. We have until 310, right? Yes, right. So you can have questions. Now let's look at the latest breakdown. Okay, the story that we started was most of the computation happens in the projection layer. Okay, now we use this technology for crossbar DAC ADC to improve the projection layers. Okay, to accelerate the projection layers. Now, if you look at this graph, the breakdown of the latency now, the part that we're spending in projection layer is so small that we have to zoom in for you guys to be able to see it. So it's now so fast that compared to everything else that is happening in the hardware, it's negligible. Now, what is the most time-consuming part of the net model now? Now it's attention lengths. That we use systolic array for that. This is the conventional technology. Systolic array is used for attention lengths, which means that we flipped the fraction. Before this, most of the computation was in projection layers. Through algorithm hardware co-design, 1-bit LLMs along with the technology it's designed for 1-bit LLMs. We can make that so fast that now it makes sense to focus on attention. Okay, so if you want to have some key takeaways here, for small language models, most of the computation happens in the attention. For large models, most of the computation happens in the projection layers. Okay, so you have to be smart about how you want to choose your technology. Now, if you use paid LLM architecture, it means that you have to first focus on hardware. If you implement our hardware or any other hardware, then you can focus on attention. Prior to this, you're only focusing on 0.3% of the computation, if you focus too much on attention. Our papers published on that scalable mathematical language modeling, this paper immediately jumped on the idea of, okay, projection layers are good, let me improve the attention X. Okay, mathmal free. And our paper was saying that, well, wait a minute, if you don't have a hardware for 1-bit LLMs, there's no point of focusing on attention X. So it's all about algorithm hardware co-design. Now, I have Gene who Peyton has seen those guys contributed to this project. Thank you for that. I'm also part of my team is here. And thank you to the team. The contribution are very important for this. To get the job done, I just here presented. A lot of these details, as you could probably tell, Gene knows better than me. If we go into details of this, and all these guys are just presenting their work. So I appreciate you guys for being here and getting the job done. If you have any questions, let me know. Oh, is that one question?
When is your like long-term or like broader plan using this just for like having this kind of like hardware and then using that for inference alongside with CPU, GPU, other stuff that we have like on in our devices or
Ideally, if, let's say I have a startup and I have enough money to build a hardware like this. Okay. You want to make a mobile technology that is heterogeneous, as a CPU, CPU, a little bit of pin, and then you have a good scheduler that looks at the intermediate representation of your workload. They go from Python to some intermediate representation, look at the computation graph of it, and then distribute the different parts, the different components, where and when it makes sense. So can I do it? Can we do it in the lab? It's very expensive. For the hardware. Do I like to have a startup to do it? Yeah, probably. Yeah, and we have filed a patent on this technology too. But that was before LLMs. Because we use this technology for CNS too. But this very similar technology has been used in CNS 2 years ago, and that's what my other students with AMD right now did that. So yeah, it's going to be interesting, but it's challenging. Having mixed signal processors and analog and digital at the same time.
is it on the like research side of it, it's like really valuable, but I was thinking about like so it should because we are talking about the energy consumption and stuff like that. So I think it should be something that is applicable.
In terms of feasibility of the implementation, it is. It's just you have to raise money to build it. If I want to, if Google wanted it, they can build it in a year. In a few months, they can have it built. So in theory, it works. In practice, it's about how much money you have to build a new technology from scratch. building chip is not, chips are not cheap.
And how do you think they'll like perform with this inference time, I mean post-training computation, like this reasoning stuff that's now like they have kind of gained more interest because they really work.
I have to look at their underlying computation. So I don't know what kind of computation exactly they're using right now. But you should remember, everything can be broken down into bunch of nonlinear operations, matrix vector multiplication, matrix multiplication. What I've been trying to do with demystifying the large language model was, it doesn't matter how you mine it, right? If you break it down to some underlying computation, and if you have a good scheduler that can see which part of this model can be implemented in what, then we can see speed up. Now, again, it's very important to also look at it from the Hamilton's law point of view. I have to look into the underlying computation of those models and see what is the mathematical operations behind them. And then you can do an Amdahl's law analysis and see how much of it can be really improved and how much of it can be low precision versus high precision. The same analysis is needed for most of them too, if they're not already like, they might be exactly like these, but with some modifications. Computation. A lot of the algorithmic innovation, don't forget, it happens during the training phase. When it comes to inference, all the models pretty much look like each other. Computation. So I should look at the underlying computations of that and then profile it to see how much improvement you can of those.
Thank you.
So, how big would be the effect of like wet binarization or dimerization on the accuracy matrix?
Yeah, so the whole point of one with L, and also we're doing some research right now in the lab that they're using one with LLMs on Raspberry Pi. Okay. Well, if you do quantization of red training, the whole point of one with LLM was that you can maintain a very good accuracy. Okay, so we do have an analysis of the Rubia score. DNS working on it, it's a work with here at NASA. You can maintain a very high Rubia score if you do quantization of red training. Post-training quantization, when you do extreme quantization, it's not going to be as good. But you don't, not only don't lose accuracy, in some cases, surprisingly, we're seeing that you also, not surprisingly, because quantization kind of work as a regularizer. So you sometimes even get better accuracy. That was a whole contribution of models that research at the field. Any other questions? Happy Valentine's Day.